Great. Good morning, good evening, good day, wherever you are, and welcome to MIT Innotherm. I'm Gang Chen, and today we have a very exciting panel. John, if you could go to the next slide. And this is on thermal desalination by membrane distillation. And we know in the past that there are a lot of interest on desalination, and this is actually really the first one we talk about in this series about desalination. So we have a very exciting panel, and I will leave the introduction of the panelists by moderator Professor John Linhart, my colleague, and I'll use one slide to introduce my colleague. John, if you go to the next slide. So John Linhart is currently a professor in a department, and he is the director of Abdul Jamal Water and the Food System Lab. This is the institute-wide lab that so it really started by John. And he is also director of Rosenau-Kendall Heat Transfer Lab. This is also where I work, so we work together in the same lab. And John's research areas are in desalination, including thermal, osmotic, electrokinetic, and his bread and butter is heat and mass transfer, thermodynamics, as I am. And his activities awards some of the selected, including International Desalination Association, serving as the board of directors, editorial board on desalination, and several prestigious awards from ASME, Alberta Award, Heat Transfer Memorial Award, Technical Committee's Globalization Medal, and is a fellow of ASME and a fellow of AAS, and the Scientific Council of the International Center for Heat and Mass Transfer. So with that, I will turn to John to introduce our panelists.
Thank you, Gang. Thank you very much, and welcome everyone. I was scrolling through the list of panelists, and there are many friends of all of us in the audience, and we're delighted that you were able to join. Our first panelist today will be Professor David Warsinger from Purdue University. David is in the Department of Mechanical Engineering, and he is affiliated with the Burke Nanotechnology Center, the Center for Energy and the Environment, and the Center for High Performance Buildings. David has been a postdoc at Yale. He's been a PhD student at MIT, and he's also worked in industry. He has received the MIT Technology Review 35 Under 35 Award, the NOMS Young Membrane Scientist Award, and he's a quarterfinalist in the DOE Solar Desalination Prize. David's research includes thermal and pressure-driven desalination processes, water energy thermodynamics, nanoscale transport physics, selective membranes and catalysis, membrane nanomaterials and nanofabrication, and gas membranes for HVAC and CO2. Our second panelist is Professor Qilin Li from Rice University. She is in the departments of Civil and Environmental Engineering, Chemical and Biomolecular Engineering, and Materials Science and Nanoengineering. She is the Associate Director of the NSF Nanosystems Engineering Research Center for Nanotechnology-Enabled Water Treatment, or NEWT more briefly, and she is a fellow of IWA. Formerly, she was an assistant professor at OSU and a postdoc at Yale. Her research interests include environmental nanotechnology, advanced membrane water treatment and reuse technologies, membranes and membrane processes, and environmental fate and transport. Our third panelist today is Dr. Guillermo Zaragoza. Guillermo is a senior researcher at Plataforma Solar de Almería. He is a professor at the University of Almería and an ambassador of Water Europe and a leader of the Renewable Energy Desalination Working Group. He has previously been coordinator of the Renewable Energy Desalination Action Group of the European Commission and a researcher at the Greenhouse Research Center of the Foundation. I'm sorry, this is blocked for me. Apologies, Guillermo. I'm having a screen issue here. He has also been a researcher at the University of Oxford and a researcher in the Institute of Astrophysics at Andalusia. In fact, we were discussing his work on the planetary energy balance while we were getting ready to start. Guillermo's research activities include the application of solar thermal energy to desalination and water reuse, and also, in particular, membrane distillation. Our fourth panelist is Professor Shihong Lin from Vanderbilt University. He has previously been a PhD student at Duke and a postdoc at Yale. His research areas include water treatment and desalination through a wide range of processes, as you can see from this list, environmental interfacial processes as well. He's received the Paul L. Bush Award, the CAPES Young Investigator Award, the DOE Solar Desal Prize Stage 1, and the Wave to Water Prize. In addition, he has received the Ralph E. Powell Junior Faculty Award. So it's an excellent group of people, and I'm really pleased that they all agreed to participate today. I'll say just a few words of introduction here about the order of our program. Professor Warsinger will talk about system architecture and key parameters. Professor Lee will talk about direct heating of MD membranes. Dr. Zaragoza will talk about performance tests of commercial systems. And Professor Lin will talk about the control of membrane scaling. For those of you not familiar with membrane distillation, this drawing gives you an idea of the process. We have a porous membrane and a saline heated feed to one side, some sort of a cooling system on the other side. A meniscus forms at the entrance to the pore, and at the meniscus, because the pore water is warm, water vapor leaves. It's pure water vapor. It travels across to be condensed as a distillate. You can see several things that are of importance immediately. You might worry about the thermal boundary layers on the feed side. You might worry about the possibility that foulants would clog the pores, or scalants would clog the pores, or cause the breakthrough of liquid. You might also worry about whether you're able to recover the energy of condensation on the distillate side. We'll hear about all of these issues and more in the course of our panel today. Now, the agenda for the event will be to have presentations by each of our speakers, taking approximately 40 minutes, and then we will have approximately 30 minutes of Q&A. If you have a question, the way you will submit your question is to use the Q&A button in Zoom, which you should see at the bottom of your screen. You can enter questions at any time, but we won't answer them until the end. We will have a moderator in the background who screens the questions and sends them over to me so that I can pose them to the speakers. If you would like to make your question anonymous, please say so when you pose the question. I'd like to mention as well that in case you have to leave early or miss part of the webinar, we will be recording this and posting it into YouTube. So with that, I will end my screen share and turn the program over to Professor Warsinger.
All right, I'm sharing my screen. Thank you very much, John. So as John was saying, membrane distillation is a thermal desalination process. What's key here and different from other desalination systems is it actually is driven by a temperature gradient across the membrane rather than a pressure gradient like you would see in some other membrane technologies. So how do you implement these systems at scale? So you actually implement these as a countercurrent heat exchanger, where the feed is preheated, comes out the other side, and produces pure permeate water in the middle. So essentially, it looks like a heat exchanger, but with the membrane thrown onto the warmer side of it to collect pure water in that intermediate channel. And that analogy to heat exchangers can be a good way to help design these systems more efficiently. In practice, this drawing is not to scale, so the lengths for these systems are often on the orders of meters to make them energy efficient, while the widths of the different channels may be on the order of millimeters. And our area is often in the order of multiple meters squared. So there's a few different configurations that are used for membrane distillation. Perhaps the most common is air gap membrane distillation, and these configurations are defined often by what is occurring between this gap between the membrane, shown in gray, and the condensing surface, shown here with kind of an orange copperish color. Air gap membrane distillation is particularly good for higher salinities. There's also permeate gap, or PGMD are the acronyms if you're reading papers in the field. And this is where the entire gap is flooded with pure permeate water. We can improve upon the permeate gap configuration by having conductive materials in the gap to minimize the temperature gradients everywhere besides the membrane itself, where we want to have our high temperature gradients. Now, there's also a few different process modifications. So in direct contact membrane distillation, instead of heating up as a preheating of the feed water, we actually recirculate the pure water in the heat exchanger approach and have an external heat exchanger. In vacuum gap membrane distillation, we have a vacuum pump that pulls water vapor out and external condensation. And similarly, sweeping gas membrane distillation has a flowing gas that goes by the cold side of the channel and also has external condensation. So what do the flows in a membrane distillation system look like? Well, it's a lot like a heat exchanger. We have a temperature gradient going from the hot side to the cold side. We have energy flowing from the hot side to the cooler side. Now, notably, there's two main components of this energy. There's the conductive heat losses, which are essentially a loss and inefficiency of the process. And there's also our water vapor evaporating and then condensing, which is our desirable desalination effect that we want to maximize in this process. And you'll see more of that later. Whenever you have heat transfer across a temperature gradient, you're going to have the generation of entropy. And we see that in these systems as well. And likewise, our exergy, or available work, is going to decrease as we have heat transfer across a temperature gradient. So there's a few different key parameters for generally defining membrane distillation systems. So we have the permeate flux. This is very simply a normalized water flux per unit area that goes to the membrane. This parameter is important because it essentially allows us to conceptualize the capital costs in these systems. Our next key parameter, and these systems are typically in the range of 2 to 10 kilogram per meter squared per hour, although some systems can reach much higher water fluxes. Our key efficiency parameter, which we use for thermal desalination, is GOR, or the gained output ratio. And we can think of this as an energy reuse multiplier that is comparing us to evaporation and condensation without any heat recovery. And so the GOR ratio itself is defined as our pure water flux times our latent heat divided by our total heat input. At a baseline, let's say boiling water and condensing without any heat recovery, but without losses, would simply have a GOR of 1. And so now we're ready for our first audience poll.
Okay, the poll should be launched, and the audience members should be able to vote. Can you see the poll?
I cannot yet. There it goes.
There we are. So we've given you a multiple choice question. Please put in your answers for it.
And so our question is, what is the highest GOR achieved in membrane distillation systems using seawater?
And the numbers are accumulating. I see about a third of the audience has voted, coming to 42%. You know, counting the number of votes is something we've gotten very good at here in the US. All right, we're up to about 60% voting. I'm going to close this in just a few more seconds, so please vote if you haven't. All right. Well, there's still scores coming up. All right, 5, 4, 3, 2, 1. Okay, ending the poll. And here are the results that we got from the poll. You can see that the answers are spread fairly broadly. The most popular answer being a GOR of 4.5. And so I'll turn this over to the others to continue the poll.
Sure. So the answer is actually the largest number, 13 plus. And in fact, this has been demonstrated by one of our colleagues on the call, Guillermo Zaragoza. You'll hear from him third as a panelist. Now, these two key parameters, the flux versus the GOR, will be a major framework we'll use to understand the performance of these systems, where our GOR we can think of as our energy or operating costs, and our flux will be our capital costs. So our next key parameter is the thermal efficiency. And this is something we can test not on a system level, but on a small coupon scale level. And it's basically describing the fraction of our heat that is actually used for desalination. And so it's essentially the evaporation heat transfer, QVAP, divided by the total heat transfer. It's capped at 1 because we can't have more than 100% of the heat going towards desalination. Typical values are ranging between 0.5 to 0.93. This is a great parameter to analyze experimentally, let's say in the lab, to understand how new materials and innovations can improve the performance of membrane distillation. Finally, our very key parameter is the second law efficiency. And this is our most fundamental universal thermodynamic efficiency, which we can use to compare membrane distillation to a wide variety of other technologies, including those that are not powered by waste heat or low temperature heat. It is defined by the minimum work of separation, given a particular water recovery, divided by how much work you actually used. For most thermal desalination systems, these values are typically between 0.1 and 10%. Thermal desalination today is not extremely efficient, and we see this a lot in issues in systems that use low temperatures and have large amounts of heat transfer. So let's graphically look at comparing the gained output ratio efficiency versus our second law efficiency, which actually includes exergy destruction. And so we can see that the second law efficiency is a strong function of temperature. The membrane distillation systems yet demonstrated vary across a wide range. They're usually kept at somewhat lower temperatures, below 100 degrees Celsius. And often when they're hybridized with other systems, especially those that can make use of higher temperatures, they can be a little more efficient. We can see that there's enormous potential for solar membrane distillation systems, but we're still early on in understanding and modeling and designing those systems. So what are the major transport resistances in membrane distillation? Well, we can visualize a membrane distillation module, and we can see that we have temperature gradients across different parts. Now, we can also map these into thermal resistances. Now, across the membrane, and if present, an air gap, those are actually desirable thermal resistances because they reduce your conduction losses that I referenced earlier. However, the temperature gradients everywhere else, such as in the feed and cold side, which can be referred to as temperature polarization, are undesirable effects that we want to minimize. We also have a mass transport challenge because we want to maximize our mass transport from the evaporation surface to the condensing surface, but we want to minimize our heat transfer through conduction in that same area. And that makes membrane distillations a really interesting heat transfer problem for optimization. And we can also have a few different condensation regimes in air gap membrane distillation, which I'll talk about shortly. So how do we model these systems? Well, there's heat exchanger approaches that we can use. There's also 1D discretized or computational modeling, where we do a kind of resistor analysis, but we break it up into many subsections over a long heat exchanger. And we can also use CFD analysis. And that's especially important for designing better spacers to reduce temperature polarization. So what kind of condensation regimes do we encounter in membrane distillation? Well, typical and the classical film-wise condensation has been the oldest studied and longest modeled, but it's fairly simplistic, especially given that real systems can be a little more complex with these very narrow geometries. We can have drop-wise condensation if we can use a hydrophobic condensing surface, and they can allow for enhanced mass transport and enhanced draining. And we can use super hydrophobic surfaces, which can even cause jumping droplet condensation, which can give very excellent heat and mass transport performance. We can also start having plug flow as the system begins to flood. And if we have too much water accumulating faster than we want to, we may go into a permeate gap mode. Now, in some cases, we want a permeate gap, but often at higher salinities, we want to create a larger thermal conduction resistance in this gap. And so it's undesirable to have permeate gap. And notably, to hold up this membrane, we often have spacers, which can cause wicking or blocking effects that can either hurt or hinder our draining of our water droplets. So what do these condensation regimes look like? Well, we can use structured nanomaterial surfaces to cause dropwise or dropping droplet condensation. We can use slip surfaces, which we've done these in my past research. And when we actually look at a condensing surface, we can see a classical film-wise copper surface versus a super hydrophobic coated surface. And we can visualize these surfaces. Here we visualize them through condensing on a sapphire plate. So we can actually see through the entire system. Here we've just simply removed the membrane module, and you can see the variation in droplet sizes and the impacts that a spacer can have. We can see how this can improve the performance by graphing our pure water flux, as well as shortly our GOR, gain output ratio. And we see that this in black, this super hydrophobic surface allowed us to substantially increase our water flux, especially at more realistic and lower temperature differences. If we can increase the mass transport resistance beyond what the current systems use, which include most of the state of the art, we can see that our gained output ratio energy versus water flux frontier curves can actually be extended with fairly modest improvements on mass transport. And I think this is a very promising area for further research. Notably, salinity has a major impact on the performance of membrane distillation. And essentially this occurs because the presence of salt in the feed water is going to reduce the water vapor pressure. And so we'll have a lower efficiency. Our maximum possibly achievable GOR, modeled here, will reduce. Notably, there's actually a peak maximum GOR we can achieve under varied salinity conditions. And this is at pretty low flux, because as we get to even lower fluxes, we have reduced evaporation from the high salinity, and thus our conduction losses become fairly important. And so these type of optimizations are key for membrane distillation design. Finally, I wanted to thank my group and my team members who help contribute to this work and our lab sponsors. And now shortly we'll go to the next talk.
Thank you, David. Sheila, it's your floor.
Share my screen first.
David, could you end your screen share?
Yes, although she can take it over. Yes.
Yes, so David talked about conventional membrane distillation technology, and this process has gained interest in the research as well as in practical application. You've seen many pilot systems that are being tested, and Guillermo will talk about these pilot studies later. But this technology still has several limitations, and I'll go over some of these limitations with you in my talk. First of all, in this process, the thermal energy is provided by the hot feed water. So your total energy input into the system is coupled with the feed flow rate. And the clean water we are recovering is therefore limited by how much feed flow rate you're providing. And so that limits our single pass water recovery to a maximum of about 18.5%. Secondly, when David talked about temperature polarization, right? The heat transfer nature of this process dictates that the temperature on the membrane surface on the feed side is going to be lower than the bulk feed temperature. And similarly, on the permeate side, the temperature on the membrane surface is going to be higher than your bulk permeate or coolant temperature. And so that reduces your effective temperature difference across the membrane, meaning here T1 minus T2 can be significantly lower than TF minus TP, depending on the hydraulic condition in the feed channel, and that reduces your flux of the membrane. And thirdly, this process, like an exchanger, the average thermal driving force is going to decrease with increasing membrane module length. And so it has been difficult to scale up this technology. And finally, because our heat is provided by the feed stream, and when the brine exits the membrane module, there's still significant amount of thermal energy in the brine. And so recovering that thermal energy from the brine is very important in improving the overall thermal efficiency of the process. Now, if we change this heating strategy instead, if we can put a coating on the membrane surface that can generate heat, either by photothermal conversion or by joule heating process, and then we can decouple our heating supply from our feed water's flow rate. And here we can independently vary our energy input. And as such, this would allow us to gain a much higher water recovery in the process. And because the surface of the membrane is hottest in the system, so we're actually reversing the temperature polarization. And because the water is being heated while it's moving along the membrane surface, and we will be able to maintain the thermal driving force better than the conventional membrane distillation process. And finally, because the feed water enters the system without being heated, and the brine carries significantly less residual heat, and therefore we can minimize the need for heat recovery from the brine. So there's two different approaches. One is the photothermal membrane distillation, which uses a coating that responds to incident light. And most of the cases, we're trying to take advantage of the sunlight as our renewable energy source. And the second approach is when you need really high energy input, high flux, we will use a electrically conducting coating to achieve electrothermal membrane distillation. So I'll briefly talk about each next. A lot of photothermal nanomaterials have been used for photothermal evaporation or photothermal distillation. Some of these have also been used for photothermal membrane distillation, and they include plasmonic metal nanoparticles, semiconductor materials, and most widely used are carbon nanomaterials because of their low cost and broad spectrum absorption from the sunlight. And some polymers and hybrid materials have also been used. There's a lot of research and that have carefully designed the structure of the coating for enhancing the evaporation efficiency. And what those are mostly designed for solar evaporation, where you would actually try to draw liquid water to the surface that is exposed to the sunlight and then maximize the evaporation efficiency. If you're trying to use the same material for membrane distillation, there's additional considerations because we're now using it in a continuous flow system where there is significant hydraulic shearing and potentially pressure as well in the system. So in the design of the coating, we need to consider very carefully the material used, the binders that are used, and the structure of the material that's applied in the coating to maximize light absorption and minimize reflection of the sunlight, and also consider the thermal conductivity, as David mentioned, that one of the loss of energy is actually conductive heat transfer through the membrane. But in this case, we're trying to transfer heat from the photothermal material to the surrounding water. So in some of these designs, we actually want materials that have high thermal conductivity. And the coating needs to be highly water permeable, and it needs to be able to distribute the heat throughout that layer. So as you can see here, by implementing different structure or different concentration of the photothermal nanomaterial, you can distribute the photons that are being absorbed across a significant depth of the membrane of the coating material. So water in the pore structure of this area of this material can be heated. Whereas if you use even higher concentration, then you can concentrate all the photons and therefore the heat within a very thin layer of the coating. And so here you have higher heat intensity, but the layer below it would not be heated. So there is a lot of optimization that can be done in the design of the photothermal coating structure. And as I mentioned before, when these structures are used in a membrane distillation process, we also need to think about the mechanical properties of the coating. And very importantly, what Professor Shihong will talk about, the fouling and scaling potential of these coating materials, because now the feed water is actually exposed to the coating, not the hydrophobic membranes anymore. So, so far, among the various photothermal coatings that have been tested, the single pass, what I call single pass score, this is the energy utilization for evaporation when you have just water passing through the membrane module one time without any heat recovery measures, ranges from 53 to 98%. So 98% is really, really good energy efficiency. So we are there in terms of photothermal materials. Now, one of the most commonly used approach to apply these photothermal materials onto a prefabricated hydrophobic MD membrane is electrospinning, and it has a lot of flexibility in terms of incorporating different types of photothermal nanomaterials into the coating structure, and naturally forms a very porous coating layer on the base membrane surface. Now, if you have a hydrophobic nanofiber coating, the air-water interface is going to form on top of the photothermal coating. So that actually reduces the amount of heat exchange between the coating material and the feed water, as well as increasing the vapor transport resistance across the membrane. So now the vapor has to transport not only through the base membrane, but also through the coating. But if you make the coating hydrophilic, then the liquid water will be able to penetrate through the hydrophilic coating completely. So you still have your air-water interface formed on the base membrane surface without adding any vapor transport resistance. At the same time, we maximize the contact between the liquid water and your photothermal coating, so maximizing heat transfer from the coating to the feed water. You can also look at how to optimize the microscopic structure of these fibers. If you have a mixed coating solution where you would electrospin the mixture of a polymer and the photothermal nanoparticle, you form a mixed matrix nanofiber. Here, the photothermal nanoparticles are embedded nanofiber, or you can use the core shell electrospinning approach. That way you can have the photothermal nanoparticles formed on the polymer fiber surface. These two different approaches results in very different properties. In the first case, the nanoparticles are embedded and covered by the polymer and therefore hinders the heat transfer from the nanoparticle surface to the surrounding water. And in the second case, your nanoparticles are directly exposed to the feed water and therefore enhancing heat transfer. And here are some of these results to show the difference between these two different approaches. As you can see in this first case, we have carbon black photothermal nanoparticles in a mixed matrix nanofiber that's embedded in PMMA substrate. And because PMMA is hydrophobic, so you form a very hydrophobic surface coating. And in the second case, we have the PMMA, the carbon black nanoparticle coated on the PMMA nanofiber surface. Let me see if I can play the video here. Oh. I was having some issue. Okay. And so because carbon black is hydrophilic, so you have extremely hydrophilic coating, water penetrates through this coating completely. And the result is that, as I mentioned before, much better heat transfer from the carbon black coated on the PMMA fiber. This red curve is the carbon black on the PMMA surface compared to the black curve, which is carbon black embedded in the PMMA fiber. At the same time, you also have significantly less light reflection from these more coarse and more rough carbon black at the PMMA fiber compared to the carbon black in the PMMA fiber. The combination of the hydrophilicity, which allows water to penetrate through the coating, the better heat transfer from the carbon black, and the enhanced absorption by reducing reflection results in or maintained the vapor transport resistance. So here you can see the core shell structured fiber had the same vapor transfer resistance compared to the pristine PVDF, which is our base membrane. Whereas if you have the carbon black embedded in the fiber, the vapor transfer is significantly hindered. And all of this combined together, you have much better performance with the core shelled structure fibers coating compared to if you have a mixed matrix fiber coating. Now, in terms of operation, how the operating parameters relate to performance of these solar membrane distillation or photothermal membrane distillation processes, there are several aspects that are quite different from the conventional membrane distillation process. As I mentioned before, because now our heat source is actually on the membrane surface, so our energy input is decoupled from the feed water flow. As you can see here, at least in the UV and visible light range, our flux is quite independent of the feed water flow rate. When you go to the IR range and near IR range, because water is a strong absorber of near IR and IR, the water flux actually decreases with increasing feed flow rate, which is completely opposite to what you would expect in conventional membrane distillation. And this allows us to use a very low feed flow rate and to gain relatively high flux, which results in very high water recovery. As you can see here, we were able to achieve single pass recovery up to 46% using just one sun unit. And another important aspect of the operation of a solar membrane distillation process is obviously this dependence on solar irradiation intensity. And so the performance measured by the membrane flux increases drastically with increasing sunlight intensity. So if you put this under a natural sunlight environment, and the performance of the membrane will fluctuate, and there is slight delay in the performance, but the performance of the process does fluctuates with the fluctuation of the solar intensity. And we've tested this process using various water sources with salinity ranging from tens of thousand ppm to hundreds of thousand ppm. And then we could always achieve very good salt removal. However, as you can see here, the average membrane flux is still relatively low. And we were able to get up to 50% of solar thermal efficiency with a maximum of 1.5 being the theoretical max. Still, that's very far away from what you would need for practical application. This tells us that if this process wants to be successful for practical industrial applications where much higher production rate is needed, we need to increase the energy input intensity, which means that we need solar concentration, concentrating the sunlight. Now, a different approach is different from solar is that we can still use electricity to provide the surface heating and to provide the high energy intensity needed for a high water recovery and a high water production rate. So here, theoretical calculation shows how the average water flux increases with surface heat input. The variable I have here for these different curves is the membrane area applied per unit volume of or per unit mass of clean water produced. As you can see, for all these cases, if you increase the surface heat input, your water flux increases linearly. So the technique we developed was that we applied a electrically conducting coating on the membrane surface. And this work was the first electrothermal MD work was published by Professor David Jaspis' lab in 2017, where they used a carbon nanotube coating bound by a PVA, and they demonstrated clean water production by putting through a electric current through the coating. And this was the first demonstration that you can actually use a dual heating material to achieve membrane distillation. And in our recent work, we wanted to enhance the water production rate and also thermal efficiency of the process. We use a very simple stainless steel mesh material, and we coated the stainless steel mesh material with hexagonal boron nitride. And this is to prevent corrosion of your dual heating material, as in electrothermal membrane distillation. The key here is to overcome the very serious electrochemical corrosion that could happen in the process. Once you have nice protective material that have good thermal conductivity, at the same time protect your dual heating material, you can, by controlling the electric current, you can actually control the energy input into your system. The higher the energy input is, obviously the higher the water production rate will be. And you can also design the system to have a spiral wound configuration that sandwich two membranes surrounding the steel mesh. And here we demonstrate that using this approach, look at the lower right corner of the slide. We compare the flux achieved as well as the what we call energy efficiency, is how much energy is utilized to generate vapor among all the energy that's inputted into the system for the different desalination technologies. So conventional membrane distillation has a very low single pass energy efficiency or single pass score. Solar thermal membrane distillation has a high single pass energy efficiency, but very low flux because of the low energy input. Was the electrothermal membrane distillation, because you can control the energy input, you can achieve very high single pass energy efficiency and high flux. As a result, we can have a very compact membrane module that give us very high water production rate. So here expressed in terms of throughput, volumetric throughput, which is volume water produced per volume of your reactor per unit time. And as a function of saltwater concentration. So as you can see here, we were able to achieve a volumetric throughput that's similar to the RO technology, but much higher conventional technologies. So these are what we are now with surface heating membrane technologies. There's significant amount of work ahead of us to improve and optimize this process. For photothermal, for both the photothermal and electrothermal, it's very important that we improve the long-term durability and the corrosion resistance of the surface coating. And there's not existing membrane modules that are designed for solar thermal membrane distillation. And so far, we have only been able to do single stage or single effect. So I think it's very important that we continue the research by designing multi-effect membrane modules for photothermal membrane distillation that would also be compatible with concentrated sunlight. Finally, as David mentioned, that the overall energy efficiency of the system really depends on how efficiently you can recover and reuse the heat. So system level optimization to maximize heat recovery and therefore minimize your system footprint are very important. And finally, for solar thermal, it's also critical to develop thermal energy storage technology so we can operate at night when there's no sunlight.
Thank you, Chilin. As we move into our next speaker, who will be Guillermo, we have another poll for you. And so I'm going to launch this poll, and I hope you can see it. Please vote. There we go. So the question is, what is the largest piloted MD system to date? Up to about 100 votes at this point. I'll give this another 20 or 30 seconds, so please do vote. And we can see the numbers are still moving a bit. We're 68%. The audience, I'm going to close the poll now, and we'll see what the responses are. So the results of the poll are in front of you now. You can see that, again, a range of answers, and the Most popular choice is 400 cubic meters per day, number selected by 37% of the audience. So Guillermo, why don't you tell us about the actual state of polling? You're muted.
Yeah.
Guillermo.
Yeah, okay, thank you. I think I'm going to stop the video to save on bandwidth and share my presentation here. Okay. So the most important aspect, it's not working. Yeah, the most important aspect we need to take into account with pilot scale modules and membrane distillation is that there is a temperature gradient along the membrane and not only across the membrane because of the size of the module. In lab scale modules, we can see for similar temperature inputs, there is not a change in the evaporator or the condensate channel. This is very little change in temperature, but in a large module, there is a change, and this actually decreases the transmembrane temperature difference and ultimately the driving force. Membrane distillation requires heat, and heat is never for free. So from the very beginning, from the early stages of membrane distillation, this is an article in 1987 from Tony Fain, latent heat of condensation, recovery in latent heat of condensation is desirable. But as it happens, heat exchangers are typically more expensive than membranes. So the goal of commercial module developers is to maximize energy efficiency by recovering the latent heat of condensation internally. And here, this is where the length of the channels play an interesting role, because as you can see here, if we extend the channels, we enlarge the residence time, and by using the feed as coolant, we can preheat the feed quite significantly and reduce the need of external heat. Unfortunately, this will also reduce the transmembrane temperature difference and the driving force, so there is a trade-off between production and heat efficiency related to the residence time and ultimately the length of the channels. How to achieve this internal heat recovery in membrane distillation modules? With plate and frame modules, is really complicated to get long channels, combining these membranes and condensate channels, and it's demonstrated by the performance results of plate and frame commercial modules, Scarab and Keppel-Seghers modules. The gore rarely exceeds 1. Only in this case, where 3 modules are coupled in series for enhanced heat recovery, the gore exceeds 1. Spiral 1 modules have it easier for internal heat recovery by guaranteeing full countercurrent circulation, and also the hot input, it's in the center of the module and the coolant on the outside of the module. So there is a natural temperature gradient and natural insulation by keeping the heat inside the module. There are several developers of membrane distillation modules, Solar Spring or Memqua, but the Dutch company Aquastil made a significant improvement by combining several envelopes in a single module. This way, there can be more channels in the module, and then the residence time can be extended for the same membrane area and feed flow rate. So that gives rise to more energy efficient modules. Now I will present a summary of the performance analysis of Spiral 1 pilot scale modules along this graph that shows the flux versus gore. And for Solar Spring modules operating in pyramid gap configuration, the results are along this line. An improvement can be achieved by deaerating the feed. Air gap membrane distillation has slightly less performance, but it can be significantly improved by extracting the air from the gap. This is the so-called vacuum-enhanced air gap membrane distillation configuration. This reduces the mass transfer resistance of the gap and therefore improves the flux with the same energy input, so also improves the gore. The multi-envelope modules of Aquastil have larger flux and gore, the shorter module has a larger flux and the long module a larger gore than the rest. But the main disruptive improvement is operating these modules in the vacuum enhanced air gap configuration, where we can see that the short module can reach to a flux almost 9 and the long module to a gore of 13.5. This is actually the best commercial performance recorded for pilot scale modules with a specific thermal energy consumption lower than 50 kilowatts hour per cubic meter, and this is better than all other thermal desalination technologies. I didn't mention before that all this comparison has been done for seawater desalination. And this module has 12 envelopes and channels 2.7 meters long. And in this case, the vacuum, the extracting the air from the gap is done with a Venturi effect suction, so therefore with a low electricity cost penalty. Hollow fiber modules can also have internal heat recovery. As a matter of fact, this concept of internal heat recovery was first implemented in hollow fiber modules by the University of Twente in the Netherlands last century. And it has been retaken and exploited by Tianjin University, who have developed hollow fiber modules with internal heat recovery, combining hollow fiber membranes with hollow fiber acting as heat exchangers. So we have the feed entering this condenser fiber and heating with the latent heat of condensation, and then the hot feed enters the hollow fiber membrane. So a similar scheme as we saw before, and the results are quite promising. With modules 1.2 meters long, the gore can be 13.8, and with modules a bit shorter, very large fluxes. Okay, keep in mind this is for 2 grams per liter sodium chloride solution, whereas the rest of the tests were for seawater desalination. But still, it's quite good. Unfortunately, this is for small scale modules, less than 1 square meter total membrane surface area. With larger modules with 2 square meters membrane surface area, the results are here, still quite promising. Also, this is for 70 grams per liter sodium chloride solution. So the challenge is to upscale these modules to larger membrane surface area, and also the electrical consumption, because the hollow fibers have larger pressure resistance, and therefore we can expect larger pumping needs and more electrical consumption with these hollow fiber modules. Heat recovery can also take place. Instead of heating the feed with the latent heat of condensation, we can evaporate more heat, so recovering the heat as latent heat. This is what MEMSIS proposed, to use the latent heat of condensation of one stage of one membrane to preheat the feed, to evaporate the feed in a consecutive effect. So they have modules with several effects reusing the latent heat of condensation for further evaporation. So multi-effect configuration, and this is in vacuum membrane distillation. So the modules are vacuum multi-effect membrane distillation. And for the pilot modules with 4 effects, we see very large flux. Of course, there are 4 effects, and the gore 3.4, I think, here. If the gore was to raise to a similar number of that achieved by Aquasteel modules, then a much larger number of effects should be part of the module. The module should have a larger number of effects, at least 13 to have 13.5 gore. 13 effects is rather unfeasible for this kind of modules. They depend on the vacuum pump to establish the flux, the feed flow rate through the different effects, and also the pressure losses will be larger, and of course the electrical consumption of such a large vacuum pump will be unfeasible, really. And upscaling, now let me finish my presentation with the upscaling of pilot scale to industrial size desalination plants. We're talking about the modular technology. So the developers build racks of modules in parallel and cluster them in a similar fashion as RO plants. So this could be equivalent to an RO train, a narrow membrane train in an industrial plant, and having a series of these racks then will give us an industrial plant. Aquasteel currently build these units with up to 20 modules that can produce more than 30 cubic meters per day with Arabian Gulf seawater. And MEMSIS build also large modules producing 12 cubic meters per day with Maldives seawater. MEMSIS built 60 cubic meters per day plant to treat RO brine in Gantut in Arab Emirates. This was soon decommissioned. And the largest existing industrial size plant is built with hollow fiber modules. Econity hollow fiber modules is a Korean, and this plant is part of the MVP research program in South Korea. These modules operate with vacuum membrane distillation configuration, and they don't have internal heat recovery. So they need thermal vapor compression for improving the heat efficiency. And the total size of the plant was 400 cubic meters per day. So most of you were right in the poll. And this plant has a total of 224 modules with rather good flux, but thermal energy consumption is also high. The GOR is not good. It's not good because they don't have this internal heat recovery. And that's all I have for today. Thank you very much. I'm looking forward to further questions and discussion later.
Thank you, Guillermo. Very interesting. We have another poll to launch at this point. And just before Shihong starts, you should be able to see this poll. The question is, which of these many approaches has not been used to prevent scaling or fouling on MD membranes? Has not been used. Remember, the question is, which one has not been used? And we are coming up to 59% of the votes, 62. I'm going to close this in about 10 seconds. Let's get your vote in. All right. So the results of the poll, the most common answer was that we have not used crystal seeding in the feed. Shihong will talk to us about some of the techniques that have been used, but osmotic backwashing, we believe, is the technique that has not been applied to MD membranes. So, Shihong, it is your floor.
All right. Thank you very much. And so first of all, I have to admit that I will be the outlier of this panel because I will be the only one who do not talk about heat transfer. Okay, so in order to capitalize all the great things that are happening in MD, we have to make sure that it does not fail, right? So here I'm trying to talk about how MD can possibly fail and how we're going to prevent that. Before we get to that, let's review a little bit what an MD membrane actually serve in the process of MD. So the role of an MD membrane, so MD is a thermal distillation process using a microporous hydrophobic membrane. Here, the microporous membrane serves as a medium for vapor transfer, so you don't want it to be blocked. And the hydrophobic membrane serves as a barrier for direct liquid transfer. And this is exactly why you don't have a osmotic backwash being one of the mitigation method, because you don't want any water to pass through the pores as liquid. Now, so there are several ways an MD membrane can actually fail, unfortunately, because it's a hydrophobic membrane. The first failure mechanism is what we refer to as wetting. So if you have some low surface tension liquids, or if the liquid contains surfactants, then it may be possible that the liquid can penetrate through these pores, and the consequence of that is that now the salt rejection would decline substantially, and the process would not be effective as a desalination process. The second possible failure mechanism is what we call mineral scaling, right? So if you have a highly concentrated stream of salt, and eventually the salt would crystallize and form this what we call scale on the membrane surface. And the direct consequence of that is, first of all, water flux, because they're blocking these pores, but it can possibly also lead to pore wetting and pore damage, especially considering the possibility of crystallization pressure that is exerted on the pores. Now, the last but most common failure mechanism in all membrane processes, not unique to MD, is what we call fouling. When you have all this organic or sometimes even oil or biological microbes, foulants, they grow on the surface and block the membrane pores. The obvious consequence of that is water flux decline, and in some cases it would also induce wetting. So fouling is a very common problem to all membrane processes and has been extensively studied. So I think the common solution is that you can do a lot of pretreatment and also put a coating layer that is very hydrophilic. And so that's something that I'm not going to talk too much about in detail, but I would rather focus on wetting and mineral scaling, which are relatively unique to membrane distillation, especially wetting. You would find wetting, you will not find the problem of wetting in all other membrane processes. All right, so let's first talk about wetting a little bit. So how do we detect wetting? So before we talk about that, let's define the 3 stages of wetting. So in the first stage, there's no liquid infiltration into the pore at all, so the membrane would look opaque. And then in this transition stage, you will have some partial infiltration of the liquid into the pore, but it has not completely penetrated through the pore. And lastly, when the liquid completely penetrates through the pore, now you end up with the wetting of the pore and the passage of the salt through the pores. And in this case, if the entire membrane is fully penetrated by the liquid, then it will look transparent. Conventionally, people monitor wetting by measuring the distillate conductivity. So if some of the pores are wetted, then you will find salts in the distillate and the conductivity would increase. The limitation with this conventional approach is that you would not be able to detect anything that is happening in this transition stage where you have partial infiltration. So recently, people are exploring electrochemical method using impedance, or also optical methods, which can actually provide you the capability of detecting this what I call imminent wetting that is going on, but none of the pore has been fully penetrated, which is actually very helpful going forward for example, developing mitigation strategy and also trying to understand the fundamental mechanism of wetting. So how does wetting occur? So there's this very important concept called liquid entry pressure, which is basically the minimum hydraulic pressure that you need to apply in order to push the water through this pore. So this liquid entry pressure is dependent on the surface tension of the liquid, the surface energy of the material, and also the pore structure like pore size and also the geometry. So the very simple criterion for wetting is that the hydraulic pressure difference between the 2 streams is larger than liquid entry pressure. Now, indeed, if you have something like a alcohol, or if you dose alcohol into a solution to reduce its surface tension, then you can actually induce instant wetting, because now this criterion is met. Or with the same solution, if now you increase the delta P, right, increase the pressure, you will also induce instant wetting. So this is basically some experimental evidence of how this criterion works. But when you have surfactant in the solution, which would reduce the surface tension of the solution, things are getting a little more complicated because of the absorption of the surfactant onto the membrane pore surface. So long story short, I just want to point out a few important observations here. First, the absorption of the surface, absorption of the surfactants to the surface would actually reduce the concentration of the surfactants at the frontier. So the liquid entry pressure at the frontier, which is where what matters, is actually higher than that in the book. Okay, and the surfactant, therefore, the surfactant-induced wetting is gradual, not instantaneous, like when you have alcohol in the solution. For example, here, if you're comparing these two cases, here's what we just saw in the last slide with alcohol addition, and here is when you add surfactant, you see that the process is much more transient and gradual. The propagation of wetting frontier occurs only when the wetted surface is saturated with surfactant. And lastly, the wetting kinetics, like based on this model, the wetting kinetics can actually be fully described by a numerical model. For example, one of the interesting observation from that numerical model and experiment is that given everything else the same, how well the surfactant can actually induce wetting, or how fast they can induce wetting, is strongly dependent on the surface access concentration, which is basically a quantitative matrix about the space the surfactant actually occupies when they absorb onto the surface. All right, so how do we prevent pore wetting? Now, there's very little we can do to in terms of pretreatment to prevent pore wetting, because it's very difficult for us, for example, to remove alcohol or surfactant as compared to remove like organic foulants. So the answer to this question is that we need to develop something called omniphobic membrane. So an omniphobic surface is basically a surface that is resistant to the wetting of both high surface tension liquid like water and low surface tension liquid like oil. That's why it has the name omniphobic. So there's this whole this beautiful theory about how we actually can make this omniphobic surface. The idea is that if you have low surface tension liquid, a cylindrical pore would actually be wetted very easily based on thermodynamics of the system. But if you can actually make some types of reentrance structure where the entrance of the pore is actually smaller than when you get deeper into the pore, then it is possible to achieve the omniphobicity. The idea is that you want to create a structure so that the water-air interface would expand as the water intrudes into the pore. So there's a very beautiful theory behind this, and actually some of those classic works that were developed at MIT. So the idea is that if you have low surface tension and you have cylindrical pore, then thermodynamically, this is as the liquid infiltrate, it would the free energy of a system would just drop monotonically. Whereas if you have a reentrance structure, then you have this energy barrier, and the non-wetted state can actually be maintained as a metastable state. So I'm not going to get into more theory, but let's talk about how these membranes well can actually mitigate wetting. So the first omniphobic membrane was actually developed back for membrane distillation application, was developed back in 2014. And following that, a lot of people start to develop different types of omniphobic membrane using different approaches. So as you can see, this is a typical omniphobic membrane where if you, regardless of the surface tension of the liquid you put on the surface, they will remain as droplets and it would not wick into the membrane, as compared to a typical hydrophobic membrane. You see that as the surface tension becomes low enough, then they would actually wet and actually wick into the pores of the membrane. So with conventional hydrophobic membrane, if you reduce the surface tension of the liquid, then you will observe wetting very easily. Like, so you see substantial reduction in the solid rejection. But if you use an omniphobic membrane, then you can basically sustain a really stable performance, even when you have a low surface tension feed solution. So, but one caveat I want to point out is that even though the definition of omniphobic membrane suggests that is resistant to oil wetting, but that was defined in air. So if you put an oil droplet in air, that is, the oil droplet is not gonna wick through the pores. But if you put an oil droplet underwater, you will still find this oil droplet to spread along the surface without wicking into the pore. So that's the difference between that and a hydrophobic membrane. But in this case, an omniphobic membrane would not give you basically the capability of anti-fouling because the pore are still being blocked. So let's switch the gear to mineral scaling, which is really important if you want to employ membrane distillation for treating hypersaline brine and maximize the water recovery. So some basic theory about like nucleation. So this is the classical nucleation theory, which says that the free energy of the system is a sum of the interfacial energy plus the bulk energy, right? So overall free energy looks something like that. As the crystal size gets bigger, you basically encounter like an energy barrier. So you need to overcome this energy barrier before you can grow big crystals. Now, so when you there are two possible mechanisms to actually change this energy profile. The first one is when you have oversaturation, when you concentrate more and more and the salinity becomes really high, you have oversaturation and it would reduce like this part of the curve. Or when you have a surface, a foreign surface, then you have heterogeneous nucleation, which would also reduce the energy barrier. And I also want to point out that the scalings are not created the same. So in some cases, for example, when you have gypsum scaling, which is very typical, they tend to form this very crystalline structure, and they can grow. This crystal can grow and become bigger and exert this crystallization pressure that may damage the pore. While in the case of silica, which is more like a gel, so they have this gelation process that would block the surface of the membrane without actually doing much into getting into the pore. So you can see, for example, from this cross-section SEM with elemental analysis very clearly that you would find some, in the case of gypsum scaling, you find some calcium deep into the membrane, but not for the case when you have silica scaling. So how do we mitigate scaling? Now, if you talk to people in industry, they would tell you that anti-scaling is the most practical approach, and which I believe is actually true. But in the research community, people are looking at trying to explore approach that would reduce the chemical use. So super hydrophobic membrane is one of the frontier, I think, for as a strategy for scaling mitigation. So a super hydrophobic membrane is simply a membrane that is so hydrophobic that if you put a water droplet on the surface, it would almost beat up like a sphere. So it has a really high contact angle and a really low sliding angle. So if you slide a surface if you tilt the surface just a little bit, then the droplet would just slide down. So with super hydrophobic membrane, the water is very slippery on the surface, and there's several mechanisms that may possibly contribute to the scaling resistance with these membranes, but I think it's very difficult to kind of quantify the contribution. The first is reduced surface area for scaling, and the second is reduced surface energy. And last but not the least, maybe the most important, is actually the hydrodynamic effect, right? So because now the water is staying only on the surface, not inside the pores, so it makes it much easier to just like for the scalings to be flushed away. Lastly, I want to point out there is synergy between material and operation approach. For example, you can try to do some air back purging, or you can try to periodically reduce the feed pressure to push away the scalings on the surface. But this approach is actually not effective if you have a hydrophobic membrane, because once these scalings form inside the pores, they form this anchor, really strong anchor, and makes this operational approach not very effective. However, if you have a super hydrophobic membrane to prevent any growth of crystal inside a pore, then this approach can become very effective. Now, to summarize, and we can actually develop membranes with different types of wetting property. Hydrophobic membrane is really bad for all kinds of reasons. So it's very easy to wet, and it's bad for scaling, and it's also very susceptible to fouling. So you can develop some kind of genus membrane with a hydrophilic coating so that you have an underwater oleophobic surface, which is really good for anti-fouling against organics or oil and stuff like that. Or you can make a super hydrophobic membrane, which is very good for scaling resistance. Or you can make an omniphobic membrane. In this case, is oil resistant and in the air, which is good for wetting resistance. Or in some cases, you can actually combine like two functions. For example, in this case, you can develop a genus membrane based on an omniphobic substrate so that you have underwater oleophobicity and also the wetting resistance for the substrate layer, like with a membrane like that, where the top is hydrophilic and oleophilic, and the bottom is omniphobic. In this case, you can achieve really good wetting resistance and fouling resistance, but you will not be able to stop the problem of scaling. So there's no one size fits all. So it really depends on like what type of feed solution you have. Fortunately, I do not think that we would have a feed solution where all this may be a big problem. So maybe some of them would be, in this case, you will choose the right membrane for that application. So to sum up, we got these challenges before we can actually arrive in practical application of MD, and we are trying to explore different approach to mitigate these problems. So much of what I have just said is actually summarized in this review papers that we recently published, and these are the authors. These are the authors from my group and also our collaborator from Colorado State. Thank you very much, and I would like to take any questions.
Thank you very much, Shihang. We will now move to the Q&A. Our background moderators have sent me some questions on my other screen here, so pardon me for looking away. First question we have from Hashib to Jilin. The question is, what are the differences between CB in PMMA and CB at PMMA? What are the ways these two are prepared?
Okay, so the CB in PMMA is a mixed matrix fiber where you mix the carbon black nanoparticle with PMMA when you do the electrospinning. So you spin them out together. And then the CB at PMMA is a cold shell structure, and you can prepare them in two different ways. If you have a cold shell electrospinning tool, and you can do that. And although it's actually quite challenging to get that interface right, to get a solvent right to form a nice cold shell structure. A simpler approach is you can also first electrospin the PMMA and then coat the carbon black particles on the PMMA fiber surface.
Our next question is to David. It is from Naimish. It is, can we use metal oxide nanofluids with super hydrophobic surfaces to enhance condensation and heat transfer as well?
Yes, and actually I have a paper that's shortly will be in review on doing just that. There are substantial fouling issues if you have a nanofluid going by a membrane that have to be dealt with, though.
We have another question. This question is from an anonymous attendee. Is the surface heating necessary if we can minimize temperature polarization by enhancing convective heat transfer in the bulk? This enhancement would limit temperature polarization, which might make the effect of surface heating less pronounced.
Right. I think the surface heating's benefits go beyond reversing the temperature polarization. The reverse temperature polarization is actually not beneficial in the surface heating process because you're losing heat to the bulk water. The biggest benefit, in my opinion, of surface heating is really to decouple the heat supply from your feed flow so that you can gain very high water recovery. You can have lower feed flow rates, and you can you don't have to suffer from temperature polarization. You can have much higher water recovery.
Question to the entire panel. What are the benefits of having a vertical orientation for MD as opposed to a horizontal orientation?
So I can just hop on this one. So especially if we're looking at an air gap membrane distillation setup, we're trying to drain out the condensed water vapor out of the system. And so we're actually getting a gravity assist as our main mode of draining out the system. Now, if you have configurations where you're not relying on a air-filled gap, it becomes much less important to have a vertical orientation.
Another question. This is a question from Patrick. In your opinion, besides desalination, is there any other application in which MD can be competitive?
Yeah, I think that in that case, it would not be called MD. It's more like membrane contactor, where you're using that to recover volatile species or remove volatile species from water. And maybe that is even more competitive than like membrane distillation, which is really crowded arena with a lot of other like competitive technologies. But I think membrane contactor is a really good direction to look into.
And of course, we assume that desalination includes brine concentration.
Question from Swapnil. The question is, can solar thermal desalination be more cost effective and produce more water than solar PV plus RO?
That's a very good question. In terms of the operating cost, which is mostly based on energy consumption, I think the solar thermal MD is still way more energy demanding than solar PV RO. But the advantage is the capital cost can be significantly lower, since you don't need a solar cell, right? You don't need a separate PV photovoltaic cell to generate the electricity. So I don't know that I don't have the definite answer, because again, really it will depend on the scale. I think at the smaller scale, the solar thermal MD might win over the PV RO combination.
A further improvement is that storing heat is much cheaper than storing electricity.
That's right.
And it's also worth noting that the thermal desal technologies can go to much higher salinities than reverse osmosis, which will be limited by the osmotic pressure, as well as the vulnerability of the narrow range of membrane materials to scaling and fouling.
So there are a pair of questions that overlap a bit. I'll try and combine them. Question is, taking into account the energetic aspects and membrane fouling and wetting, what will be the most suitable configurations for membranes and modules at the industrial scale? Or more broadly, what are the biggest challenges for implementing MD at medium and large scale?
I can jump in and mention that the developers that have reached are close to the industrial scale all use air gap membrane distillation configuration. And that makes sense considering that the applications are for feeds that RO has problems with, so high salinity. So that makes sense to use air gap configuration. And the challenge really is electrical consumption. Demonstrate that electrical consumption is competitive. The thermal energy consumption has already been demonstrated to be competitive and better than other thermal desalination technologies. But electrical consumption presumably is not high, but it has to be demonstrated at large scale, because a small scale, of course, is not representative because of the low efficiency of small scale pumps and that.
I just want to add to that I think the vacuum air gap membrane distillation variant, which reduces the pressure in the air gap that Guillermo's been using, is particularly promising of those configurations. And I will say, I believe that for high salinities, the air gap configurations are best, but for lower salinities, the conductive gap membrane distillation configurations may win out.
Of course, I meant the vacuum enhanced. My air gap includes the extraction of air from the gap.
Another question, how does salinity affect the total mass output while using membrane distillation?
In the photothermal process, it has a very large impact because the driving force is very small to begin with. With concentrating sunlight, I think the impact will become smaller. because the impact is mostly in the change in the vapor pressure of water with salt concentration. So if you have a large driving force, and if that vapor pressure change is relatively small compared to the driving force, and the impact is relatively small. But it does have a major limitation on the water recovery, because ultimately it's the scale formation that limits your water recovery.
Another question we have, this is to David. Could you explain why the experimental data for super hydrophobic surfaces is not as good as water gap MD?
Sure. So in that case, we were only looking at the water flux and not the overall energy performance. So you actually have a reduced conduction in the permeate gap system. So you're going to end up with a lower thermal efficiency and a lower GOR, but you'll have enhanced flux because there's going to be better heat transfer and a larger temperature gradient across the membrane itself. But that's just flux. Really, you want to consider the flux versus GOR trade-off in any of these systems, which we showed you with a number of our figures. I also want to note on the last question, one of my slides showed the GOR versus flux frontiers for increasing salinity. And we can see that we pay a large penalty with that whole frontier moving back as we get to higher salinities.
Here is a question to Qilin. I wonder if your lab has done any work or considered optimizing the geometry of the electrospun fibers. For example, thickness and pore size might affect performance.
Yes, we've done some in an industry-sponsored project. Porosity definitely has a major impact, and thickness is really a strong function. The optimal thickness depends on your photothermal nanoparticle density. As I think I showed a simulation of where photons are absorbed throughout the coating layer. And if you have high density of the photothermal nanoparticle, then the photons tend to be concentrated on the top layer. And then you wanted to, in this case, use a thinner coating so that the pore water is all heated and you don't have a layer of stagnant water that's not being heated. But the work we've done is still quite limited. So yeah, no, we haven't completed that optimization work yet.
Here's a question, a challenging question, I think. At least it's a challenge to the membrane aspect of membrane distillation. The question is, if we eliminate the membrane, but still have an air gap, could we get comparable performance, but without scaling issues?
Yeah, I think I've seen papers like trying that approach. I think the one appeal is of all membrane systems is that you can have a really large membrane area or specific surface area for mass transfer. So if you were eliminating the membrane, then you basically lose that advantage. But I think it's not a bad idea to try to like really just get rid of the membrane, because that would really address a lot of the possible failure problem mechanisms that I just mentioned.
Yes, but it's very tricky because a major benefit, we get very good heat transfer because we have very close, only a few millimeters between our hot and our cold streams. And so the membrane is just acting to separate out the pure water from the salty water. If you can find a way to maintain very small gaps and keep them separated, perhaps with gravity and some really clever designs, then maybe there's some potential. But it's very challenging, and I haven't seen a design that can actually achieve the good heat transfer and heat exchanger-like performance that also avoids a membrane.
So maybe just like a super hydrophobic mesh with this like pores with hundreds of microns, they may retain the droplets from getting back to the feed.
And perhaps if you were able to take the water out with other clever techniques or absorb them into a condensing surface and wick them out or pump them out, there may be ways to do it.
So we'll take just one or two more questions because we're coming toward the end. This is a question from Mustafa. Can the membrane distillation concept be used to extract water vapor from moist air instead of extracting it from feed water?
So I would say that you need a saturated solution in a temperature gradient If you already have moist air, you don't need the membrane itself to separate out water vapor. However, there is an emerging field on a different class of membranes that are actually H2O separation membranes that can be used for very effective extraction of water vapor from the air. And it's one of the research thrusts I'm working on.
In fact, I'll add on to that our last Inotherm webinar on HVAC systems included some discussion of moisture separation membranes to reduce the condensation load in HVAC systems. I'd refer you to that. It was a great set of talks. This will be the final question. Do you think there is a future for large-scale applications of hybrid thermal desalination? For example, MED plus MD.
I don't see the benefit of it really, because MED has to work at large scale, and it achieves similar things than membrane distillation. So I don't see how membrane distillation would contribute to MED. Of course, coupling RO and membrane distillation, I see a very bright future for that. But coupling it to other thermal desalination technologies, I don't really see the point.
So I actually think there is potential. And if you can think about membrane distillation, is basically a countercurrent heat exchanger. In MED, MVC, et cetera, we do have countercurrent heat exchangers. Any situation where we could have one of those heat exchangers, we could swap out for an MD system and enhance the recovery. I think we actually could be improving the efficiency of those processes doing that.
Well, I want to thank everyone. I will apologize to anybody whose question we haven't gotten to, but we've reached the end of our time. I want to close on just an announcement of our next Inotherm webinar. This will be on December 8th, 3 weeks from now. We will not have a webinar during the preceding week, which is the US holiday of Thanksgiving. That upcoming seminar will be on direct energy conversion by thermal photovoltaic and thermionic technologies. A great set of speakers lined up for this. Gongchen will moderate. So this webinar will be posted to YouTube fairly soon. We will also post the questions, including the ones that we were not able to get to. And so those will be available there. Of course, I encourage you to write directly to any of our panelists if you have further thoughts or comments. And I want to thank all of you for joining us today. And I'd particularly like to thank our 4 very distinguished speakers for their excellent presentations and for making the time to share their ideas with all of us. Thank you and have a good day.